So just a basic review of your chemistry for the last few years. Atoms, molecules, and hybridization. So obviously atoms are composed of protons, neutrons, and electrons. Electrons are the guys that do all the dirty work. They're involved in the chemistry. It's the easiest part of an atom to interact with, and the electrons can interact with other atoms. Compounds and molecules, it's the combination of atoms that create the compounds and molecules. The protons and neutrons are essentially locked into a specific orientation that gives the shape of the molecule itself, but the electrons are free to interact and roam around all the other atoms. So they're not just static on one atom, they're actually interacting all throughout the entire molecule and moving around. So in terms of review, if we were to look at a Lewis dot diagram to help us determine the shape of a molecule, we're going to look at something like ammonia, where we've got 1 nitrogen and 3 hydrogens. We look at the periodic table in group 5. We have 5 valence electrons for nitrogen, 1 valence electron for each hydrogen, which gives us a total of 8 valence electrons involved in the compound for the formation of it. When we combine them together, we want to make sure we follow the octet rule. So we need to have 2 electrons for each hydrogen, and we need 8 electrons around the nitrogen. And that satisfies the octet rule and the valence. So in determining the shape then, we can automatically assume that there's a tetrahedral type shape. If we've got 3 atoms in a non-bonding pair, we put them in this type of shape with the non-bonding pair up top here like this. Ultimately this is a tetrahedral shape, but because the non-bonding pair just occupies a space by itself and there's no atom there, we call this a pyramid shape. So the non-bonding pair just takes up the space up at the top. If there was an atom here, as in ammonium ion, so NH4+, then this is a tetrahedral shape that this would take, and there would be a plus charge on the nitrogen. So recalling our orbitals, so based on atomic orbitals, we have the s, p, d, and f orbitals that we can deal with. For organic chemistry, we mainly deal with just the s and the p orbitals because we're only dealing with the second row. And the reason why these are important is because they combine together to produce our molecular orbitals that we're going to be dealing with. And the molecular orbitals we're interested in are sp, sp2, and sp3 molecular orbitals. sp3 hybrid orbitals, they contain 4 orbitals combined together, 1s and 3 p orbitals. They combine to form a hybrid called sp3. And these orbitals try to get as far away from each other as possible. So 109.5 degrees is the perfect tetrahedral shape and the most equidistant space for these orbitals to get away from each other. And this is typically seen in the formation of single bonds. So if you ever see single bonds or a large chain of single bonded molecules, then it's most likely sp3 hybrid. sp2 hybrid orbitals involves 3 atomic orbital combinations. So we're looking for 1s and 2 p orbitals. And what that means is we have 1 p orbital actually left over. So the 3 orbitals combine to form 3 molecular orbitals. Those molecular orbitals try to get the furthest away from each other as well. 120 degrees is the best that they can do. And so they form this sort of planar, flat planar triangle structure around the center of a p orbital. Now these SPs can actually be used to form single bonds, and this p orbital is left over to actually interact with another p orbital and form a double bond. So sp2 hybrid orbitals overall you can see used in the formation of double bonds. sp hybrid orbitals, so we're only using 1s and 1p orbital, which means we have 2p leftovers, p orbitals left over to help contribute to bonding. So we end up with an sp hybrid, which will end up doing the sigma bonding, and leaving the 2 p orbitals left over to contribute to a triple bond. So whenever you see a triple bond, these sp hybrids are used in the formation of these triple bonds. And here's an example of a double bond. So essentially, I took the picture we had previously and just sort of reversed it. But the first overlap we would get is we would get the sp2s to get a positive overlap, and we'd have a sigma overlap right here. And then the secondary overlap would be these 2 p orbitals. We'd get an overlap here and an overlap here. And this overlap, both this and this, combine together to be called a pi orbital overlap. This is a sigma orbital overlap, a complete overlap. This is a pi orbital overlap. Reason being is this side of the node, if they combine together, would be a positive overlap, and this essentially here would be a negative or the opposite type of node, opposite type of the bond of the orbital coming together. So there's actually a node that runs right through here, and that's what gives rise to this pi orbital. So a sigma orbital here from the positive overlap, and a pi orbital from the p orbitals.